We're going to pick up here in the middle of chapter 5. We talked about electron configurations, and now we're going to look at how the quantum mechanical model explains a lot of things. So we know that the periodic table is named the periodic table because of the properties of the elements recur in a periodic manner. The reason that they do so is because of the number of valence electrons. The number of valence electrons is periodic. We saw that. It was a whole week ago, but we looked at that. Group 1A has 1 valence electron. Group 2A has 2 valence electrons. The reason that the group 2A elements have a lot of things in common is because they all have 2 valence electrons. Yeah, so I think I said that. So let's look at the noble gases. How many valence electrons does neon have? 8. So this is the electron configuration of the highest occupied principal energy level. So 2 plus 6 is 8. And argon, 2 plus 6, 8 valence electrons. Krypton, 8. Xenon, 8. Radon, 8. Of course, here's helium. Helium is almost like a twin brother to hydrogen. He's this little guy who gets away with breaking all the rules. So here he is over in group 8A. He doesn't have 8 valence electrons. He doesn't even have 8 electrons. He only has 2. But what's important is that highest occupied level, which is only the first level, is full. For neon, the highest level where there are electrons is the second energy level, and it's full. It's like a magic number. These elements do not react easily because they don't need to. They're good by themselves. They don't need other elements to complete them. And so they're very stable and they don't react. In fact, some of these elements, like helium, there are no known compounds with helium. Nobody's found one. Helium does not react with anything. It just does not react. Because it is so stable already, there's no reason for it to react with anything else. Let's look at the alkali metals. The alkali metals are one column over from the noble gases. I actually made a circular periodic table in GRASP on Friday, and I should have brought it in. It also doubles as it's almost like a Burger King crown. It's really cute. But you can look at the periodic table as being really more of a cylinder, just like you look at a map of the Earth. It's flat, right? But the Earth isn't flat. It's a sphere. Well, you can't draw things like that on paper, so we flatten it. You cut it and you flatten it. The periodic table can be thought of that way too. Lithium, question. Kind of like a spiral, yeah. I'll bring it in later and show it to you. So lithium, I'm looking up at the periodic table and trying to find my pointer. It's not on there because I'm looking at the wrong thing. Lithium has 1 more electron than helium, right? Sodium has 1 more electron than neon. These alkali metals all have 1 valence electron. They are extremely reactive because they are very close to that stable energy configuration that the noble gases have. If sodium loses that 1 valence electron, it has the same number of electrons as neon. That's an especially stable position. And so it will do that quite easily. Sodium will react with all kinds of things because in doing so it lowers its energy. That's the scientific explanation. I think of the noble gases as being the in crowd in high school that everybody else, secretly at least, wanted to be like. You want to be in that crowd. And so what I observe in my kids is that they tend to dress like the cool kids, right? You go to school and everybody's like, oh, we need to be individuals, we need to express ourselves, right? And they're all wearing the same kind of sweatshirt because they want to be the same on some level. So sodium wants to be like neon. And it can do so by getting rid of this 1 extra electron. This is the ugly sweater that sodium's mother made him wear to school. And if he takes that off, then he looks like the cool kids. You're laughing. Good. Because this is supposed to be stupid and silly, because then you might remember it. So they can obtain that noble gas electron configuration by losing a small number of electrons. I'm not sure why gaining is in there. It shouldn't be in there. Other things do that. Well, I think it was this statement here. This is meant to be more general. Elements that are close in electron configuration to the noble gases. This is one example. We'll see the halogens are another example. The alkali metals, though, lose an electron. When they do that, they have the same electron structure as the noble gases. On the other side of the noble gases are the halogens. So fluorine has an electron configuration that ends in 2s2, 2p5, one short of that stable noble gas configuration. So fluorine is going to easily react in a way where it will gain one electron and get that stable configuration. So the halogens are also very reactive. The halogens form anions with a -1 charge. We observed that and learned that just kind of as a rule, but this is why. The alkali metals, they form +1 ions because they lose one electron to get that stable electron configuration, and that makes them a +1 ion. So the halogens gain an electron because that's the easiest. There are many metals and nonmetals that only form one ion, the main group elements for the most part. The charge on that ion is predictable from the position of the periodic table, and we learned how to predict that. Group 1 forms +1, group 2 forms +2, group 7 forms -1, group 6 forms -2. The reason they do that is because when those atoms form ions with those charges, they have the same number of electrons as a noble gas, and that is an especially stable energy situation. In your book, they misnumbered the periods here because they left hydrogen off. They left the first level off with hydrogen and helium, and somebody wasn't thinking, and they just started with number 1. So you might want to fix that. Dumb. So group 7A forms a -1 ion. Not because, as I told you earlier, you count back from here saying 0, -1, -2, -3. That is a trick that gets you the right answer, but that doesn't explain. The explanation is these guys gain one electron, form a -1 ion, because that gives them a more stable electron configuration. The group 2A metals will lose 2 electrons to get that noble gas electron configuration. All of the elements are trying to get that noble gas configuration, and that explains so much of their behavior. If we look at the electron configuration of anions, remember, anions are formed when you gain an electron. It has a negative charge, but that means you got an extra electron. They're going to gain, the nonmetals are going to do this, they're going to gain enough electrons so that they have 8 valence electrons. 8's like a magic number for elements. 8 valence electrons is what we're shooting for. So when that happens, the s and p orbitals of the valence shell are full. Bless you. So we look at sulfur. Here's the electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. Remember the valence electrons are the ones with the highest N. Right? So that's these guys right here. 6 valence electrons. It wants 8. The easiest way to get 8 is by gaining 2 electrons. It could lose the 6 that it has, but it's easier to just gain 2 rather than lose 6. So if it gains 2 electrons in this 3p level, we get 3p6. This is the same electron configuration as argon. Does sulfur become argon when it gains 2 electrons? No. What's different between the sulfide ion and an argon atom? The electrons are the same. What's different? The number of protons. So in chemistry land, my fantasy world, I see the electrons as being similar to the clothing that we wear. It's fairly easy to change your clothes, right? You can put a sweater on, you can take it off. You can't change who you are. The protons, the nucleus, is the core of the atom. That doesn't change. The number of electrons can change, but what it is doesn't change because the number of protons never changes. Cations form when a metal loses its valence electrons. It's going to lose all of them. The main group ones are. This process is always going to be endothermic, though. You say, well, they wanted to do that. It should just happen. It should be exothermic. Well, no, it's pretty easy to do, but it still requires energy to take those electrons off. Let's look at magnesium. Here's the electron configuration for magnesium. It's got 2 valence electrons. To get 8 valence electrons, it could gain 6, or it could lose 2. Losing 2 is easier. So it will lose its valence electrons, become a magnesium 2+ cation. It lost those guys, so what's left is the same electron configuration as neon. It does not become neon. It's still magnesium. But on the outside, it looks like neon. It's like if you're not one of the cool kids, and I was not one of the cool kids in high school. I just kind of stood back and watched everything that went on. But you can dress like one of the cool kids. Does it make you one of the cool kids? Unfortunately not. It's just not that simple. But you can look like one, and you can fool some of the people. So, any questions about that? No?